Hello everyone, welcome to my talk on code quality measures used by machine programming systems. My name is Niranjan Hasabnis and I work as a research scientist at Intel Labs, where I work on applying AI techniques to solve problems in software engineering. Now, before I jump into the work, let me briefly talk about the notion of machine programming if you're not familiar with it. Machine programming is a notion introduced by our group in 2018 paper that combines AI and formal methods to automate software development. It introduces three pillars, as you can see from the image, that we argue are critical to machine programming. More importantly, we observe two key trends that fuel machine programming. First is vast amount of open source code hosted on sites such as GitHub and GitLab. And second is powerful compute resources such as CPUs and GPUs that are available now to process that data. Already there are a number of machine programming systems. I will briefly talk about two of them. First is Aroma, which is a code recommendation system developed at Facebook. It assists developers in finding snippets of code relevant to certain APIs that they may be interested in. As against syntax-based matches, Aroma applies AI techniques and considers code context to suggest more relevant code snippets. Second is Control Flag, which is our proactive programming error detection system. Specifically, it mines open source code repositories to understand typical programming patterns used by developers and then considers any deviation with respect to those typical patterns as anomalies or errors. At a higher level, instead of relying on manually programmed rules to detect such errors, Control Flag applies AI techniques to automatically learn those rules using open source repositories. It has found subtle errors in several popular open source projects so far. You may have heard about GitHub Copilot as an intelligent programming assistance system. Given a prompt or a description of a function, it suggests code snippets in real time. Now, I won't get into the details here, but just wanted to mention that it is also a machine programming system. As I discussed earlier, all machine programming systems use open source code as training data and learn certain properties from it. Just to clarify, these systems can also be trained on closed source code if privacy is a concern. The key question when using open source code as training data though is, how do existing M-based systems select code repositories for training purpose? And what is the quality of those repositories? This is important because we all know the importance of quality of training data from the machine learning research. A quick look into the details reveals that these systems are using unconventional measures to select code repositories. For example, quoting directly from the Aroma paper, we ensured the quality of the corpus by picking projects that are not forked from other projects and have at least 5 stars. Similarly, quoting directly from the Control Flag paper, we chose top GitHub repositories having at least 100 stars. Use of GitHub stars as a code quality measure is strange, given that GitHub stars is established as a popularity and not a quality measure in software engineering community. And funnily enough, people have tried GitHub Copilot on various unusual prompts to receive hilarious responses, as you can see from the slide. In a nutshell, we observed that existing machine programming systems are using unconventional code quality measures to select code repositories for training. And this observation led to our quest in this study. Concretely, contributions for this study could be summarized in 2 points. First, we leverage existing research from software engineering community to develop a framework that we call GitRank to analyze if code quality measures impact performance of machine programming systems. GitRank is published already and is open source also. Second, we select Control Flag as a candidate machine programming system for our study. We apply GitRank to systematically study impact of different quality repositories on the performance of Control Flag. Before we jump into our study, let me briefly talk about GitRank. This is because the code quality measures used by GitRank would impact the outcome of this study. When we started the study, we investigated existing publicly available open source frameworks that can rank code repositories. But unfortunately, we did not find any framework for our purpose. The closest we found was npmjs.com, which is a framework to rank JavaScript packages based on 3 criteria, namely quality, popularity, and maintainability. This is why we have implemented GitRank from scratch. We have nonetheless derived insights from several existing frameworks. Now, the goal of GitRank is to rank code repositories based on commonly used measures in software engineering community, such as quality, popularity, and maintainability. We derive these measures and their categories based on existing research in software engineering domain. Now, I won't get into the details of every measure for the sake of time. The paper explains them in detail. Moreover, since this is a preliminary study, selection of measures is also a bit ad hoc currently, but we are planning to investigate more systematic approach soon. Along with existing papers in software engineering community, we have also derived insights from popular code quality models such as ISO 25000, also known as Square in short, or SQOSS model for source code measures. Given a list of repositories to be ranked, Git rank obtains quality, maintainability, and popularity score of every repository first, and then ranks them based on their normalized scores. I won't get into the details of Git rank for the sake of time, but again, the paper has the details and the formula that we use for ranking purpose. Eventually, it outputs a ranked list of those repositories in HTML format along with the score breakdown. Finally, GitRank is already published as a research paper this year at Mining Software Repositories Conference, and we have also open sourced it at a URL mentioned on this slide. Feel free to check it out and let me know if you have any feedback. We already have a couple of folks who are interested in extending it further for that purpose. Now, in this preliminary study, we take control flag as a candidate machine programming system and apply Git rank to study effect of different quality repositories on control flag. The finding from this study could thus be specific to control flag, and we discuss about their generalization as a future work in the paper. So for this study, we devised two research questions as a part of our study. First research question evaluates impact of code quality measures used by Git rank on the performance of control flag. Specifically, we evaluate if top quality datasets obtained using Git rank perform better on control flag than bottom quality datasets. Second research question evaluates impact of unconventional code measures used by control flag itself. It is again the same formulation. We evaluate if top quality datasets obtained from repositories having more than 100 stars perform better than bottom quality datasets on control flag. We generate three different datasets to answer those questions. Now, logically speaking, we would need to generate two datasets for every question, so 4 in total. But we found that we could share one dataset across both the questions. Specifically, for control flags repository, from control flags repository, we obtain a list of 500 repositories having more than 100 stars. This is to avoid any effect of number of stars as a measure on the first question. We then rank those 500 repositories using Git rank and divide the ranked list in half. We call the top half as DT1 and the bottom half as DB1. As the second research question pertains to the number of stars as a measure, we generate one more dataset using 250 repositories having less than 100 stars. We call it DB2. DT1 or DB1, both having more than 100 stars, can be used directly as a top quality dataset for the second question. We use DT1 in our study. Finally, we devised three different tests to evaluate effect of those datasets on control flag performance. First test is, of course, the output of control flag. We call it end-to-end test. Train control flag on the chosen dataset and then evaluate the train model on a candidate repository. Second test is independent of control flag. We have devised a graph analytical test by visualizing training dataset as a graph. I will talk about it briefly in the next slide. Third test is more of a qualitative one. We manually inspect all the datasets to check if top quality datasets contain examples of good programming practices. Recall that control flag mines programming patterns from code repositories. A bad pattern would typically indicate bad programming practice. Our graph analytical test is devised as a general purpose test to evaluate confidence or trust in the dataset. Given that control flag mines patterns from different code repositories, we can visualize its training dataset as a directed graph where we have repositories on the left-hand side and patterns on the right-hand side. And a weighted age from a repository to a pattern indicates contribution of that repository to that pattern. The number of patterns contributed by the repository would be the weight of the age. Given such a visualization, we evaluate this data set from two perspectives. We check if patterns are peer reviewed, as in we check that they are contributed by several repositories and not only a few. This is summed up as using int degree of patterns and summed up as a C degree. We then also check that patterns are uniformly contributed by the repositories. This is represented using CSTDev. We then combine C degree and CSTDev to come up with final score. I have glossed over some of the details here for the sake of time, but feel free to check the paper in case you are interested to find more. Finally, coming to the evaluation results, they are presented in the paper in detail, so I'm not expecting you to read the numbers in the table, but I will briefly talk about our analysis of the results. What we found was that the results convey a mixed story. Top quality data sets in the first experiment DT1 wins an experiment but loses on the second experiment. Recall that we are using DT1 in both the experiments as a top quality data set. In other words, we see positive correlation between code quality measures used by Git rank and control flags output. But we also see negative correlation between code quality measures used by control flag and its output. In other words, we see that GitHub stars is not a code quality measure. Nevertheless, we also stumbled upon some open questions that we plan to answer as a part of future work. For instance, some of the measures used in Git rank, such as the number of compilation errors, would not affect control flag's output, as control flag can handle code with compilation errors. So the measures to be considered for control flag and other MP systems would need to be fine-tuned from a generic list of code measures. We have discussed our plan for the future work in the paper. So to summarize, what we discovered in this work is that existing machine programming systems use unconventional code quality measures such as number of GitHub stars, and through our evaluation on control flag, a candidate machine programming system, we found that the number of GitHub stars does not directly correlate with the code quality. This is in line with the observation reported in several software engineering studies. On the other hand, we found that measures used by Git rank have higher correlation with the control flag's performance, and we believe that this finding provides a direction to explore this problem further. So that's all I had for this study so far. I'll be happy to answer any questions you may have. Thanks for listening to my talk.